So far, we have discussed on the equilibrium criterion for different systems like adiabatic system and general system. And also we have taken one sample equation, general sample equation, uh, that is A plus B is equal to C plus D. On that equation, we had applied the chemical equilibrium criterion and derived the expression for the equilibrium constant and also the standard state Gibbs function change that we have done. And also we have computed the entropy, that is, sorry, the Gibbs function change, how to calculate that, because part of that we need to get from the table and part of that we can just calculate knowing the two pressures, that is starting pressure and the equilibrium pressure. So from that we can calculate the final Gibbs function that we need to use in the equilibrium criterion. So that we have done, and also we have solved one problem in the last class. Okay. Now, what we will do in this class is that I will just show you three things on the screen. Here you can see that the equilibrium constant in terms of pressure, that is equilibrium constant Kp in terms of the partial pressures are is expressible in three ways. That is Kp in terms of pressure, partial pressure, Kp in terms of the standard, uh, that is Gibbs function, standard state Gibbs function change, that is delta G star. Delta G star is basically, what is star? Here star means basically at standard pressure, and temperature is the temperature at which the reaction is taking place. So that temperature is any temperature at which the reaction is taking place, starting from the reactants up to the equilibrium condition. We are considering that the temperature is constant, or and that is the specified temperature. And for pressure, since the pressure that is at 1 atmospheric value, the tabulated data is available. So at any other pressure, that is actually the partial pressure at which the component is existing in the mixture. The mixture pressure is the total mixture, the total pressure, but individual component wise, they are existing in their partial pressures. So from the standard state, that is 1 atmospheric, to the partial pressure, how the uh, change of Gibbs function takes place. So that we have done. And here that delta G star represents the Gibbs function values at the standard state pressure and the specified, or the temperature at which the reaction is taking place. That we have done, that we need to understand. Okay. So here that star is for the 1 atmospheric pressure, and this T is the temperature at which the chemical, that is the reactants, starting from the reactants up to the chemical equilibrium condition, this is the temperature at which the reaction is happening. And this is the same absolute temperature. And the third one is the equilibrium composition, equilibrium uh, equilibrium constant in terms of the equilibrium composition. So equilibrium constant in terms of the equilibrium composition. Okay. So now we will look into some observations here. Uh, Here we will look into some observations the about the equilibrium constant Kp for ideal gas mixtures. Okay. Now here you see that Kp, as we have seen in the last class also, what is Kp? If you just follow these three expressions, one is this Kp here, this one, the second relation. Here you see that Kp is expressed in terms of delta G. You see that delta G star T, and this is T, RUT. So you see that the whole right hand side is temperature dependent only, and there is no trace of pressure because 1 atmospheric pressure, this is fixed pressure. So pressure is already fixed. Therefore, the right hand side depends on only temperature. Okay, so for a particular chemical reaction, obviously, the right hand side depends on temperature only. Now, therefore, Kp is independent of the mixture pressure. We can see from this. So one thing that Kp of a reaction depends on temperature only. This can be concluded. Another thing is it is independent of the pressure of the equilibrium mixture and is not affected by the presence of inert gases. So second point, that is it is not affected, that is Kp, the value of Kp is not affected by the presence of the inert gases. That is another observation. So how to basically prove it? You see that delta G is what? Delta G is the standard state Gibbs function change. Change from what to what? Change from the reactants, starting from the reactants up to the products at the equilibrium condition. Next, so if there is an inert gas, then inert gas will not basically take part in the reaction. Therefore, whatever change of that from the starting to the end, there will not be any change. There will be Gibbs function for that, but the change of that value will be 0. And also, what is the contribution of delta G? You can see that contribution of delta G is here. You see this one. So individual terms, even if there is some inert gas in the reaction, then that neither the mole fraction, neither the number of moles nor the Gibbs function standard state value will change. Therefore, the total Gibbs function also will not change for that inert gas. So inert means it will not take part in the reaction. Therefore, its number of moles will also not change, and also its value, that is Gibbs function value, will not change. Therefore, the total change in the total change of the Gibbs function, the contribution of inert gas will be effectively 0. Okay, so since inert gas is not undergoing any chemical reaction, so the change of Gibbs function of this will be 0. Therefore, even if there is some inert gas in the chemical in the mixture, equilibrium mixture, it will not basically affect the value of Kp. Okay, so because you see that if I try to understand the Kp value from this. Okay, either Kp value from this or this or from this. So because delta G will not be changing by the presence of inert gas, so it will not change. That means inert gas presence will not change the value of Kp. So first try to we try to understand this. This okay. Thus, at a specified temperature, the following reactants, all the following reactants that you can see will be having the same Kp value. For all these reactions, we'll have the same Kp value. Because you see that for all these, the chemical reaction basically are the same. For all these, try to see that the chemical reactions are basically the same. Only thing is that what are the differences you try to follow? That here in all these reactions, hydrogen and oxygen are combining to produce H2. Okay, here also you see maybe the amount of oxygen here is different, but you see that ultimately amount of H2O, number of moles of H2O, that is same. Only thing oxygen is excess here. So this oxygen amount will be cancelled in the numerator and the denominator, from the numerator and the denominator. Also this 5N2 that will be also cancelled from the numerator and the denominator. Okay. Now also one thing we have seen that the pressure, that is the mixture pressure, will not affect the value of the equilibrium constant. Okay. Now one point may be coming in your mind, that you see that the first, in terms of the partial pressure, that Kp is dependent on the partial pressure. Again, partial pressure means what? Partial pressure Pi is Yi into total pressure. So if the total pressure is changing and partial pressure will also, the total pressure is changing, the partial pressure will also change. Okay, but the stoichiometric coefficients are unchanged. So if the partial pressure changes, then how can the equilibrium constant remain constant? That may be a question. Okay, we will see later that how the partial pressures will adjust themselves there, so that the Kp value remains constant. Because Kp value is constant, that is obvious from this relation, the second relation, that it depends on temperature only. It does not depend on pressure. That is obvious. But there may be a confusion that if the total pressure changes, then partial pressure will also change, and therefore it may be dependent on pressure. But we will clarify that in one next point. So till then we will wait. One thing that we have to observe is that for all these reactions, the Kp values are same, because here the basic reactions are same. Basic reactions are same, and only thing is that there are some inert gases presence of inert gases. Inert gases means here you can consider the non-reacting gases here. So they are basically inert to the particular reaction. So here the inert gas presence will not affect the Kp value, and also the total mixture pressure will not affect the Kp value. That is the observation here. Okay. So is this point clear? That is, the Kp value is not affected either by the total mixture pressure or by the presence of inert gas, because it depends on temperature only. That conclusion is derived from the second relation. Okay. Next, Second observation. Second observation is that, so that may be a question that may come in your exam, that for all these, whether the KP values are same or different. So you have to understand and then answer. Okay. So since the total pressures are changing, so it may be confusing you that the KP value may change, because KP value directly depends on partial pressure, so it may change. But we know that it depends on temperature only, and since the temperatures are same, therefore KP values will be same, irrespective of the presence of inert gas, or the presence or the pressures are different, total pressures are different. Okay. Next. The Kp value of the reverse reaction is 1 by Kp. That is quite obvious, because you see that Kp depends on what? Kp depends on the ratio of the pressure, partial pressure raised to the power of power by the stoichiometric coefficients. Now, for a particular reaction, if I just reverse the reaction, stoichiometric coefficients will remain the same, and also the partial pressures in a particular chemical reaction. What happens? Particular chemical reaction, can you tell when the chemical reaction is in equilibrium? Okay, whether it is reverse or the forward reaction, the composition will remain the same. Only thing that our treatment, that is one, which one actually was the ones which were actually reactants. Now for the reverse reaction, they will be products, and the ones which we considered as product for the forward reaction, now they will be actually the reactants. So what Kp will be basically now in the, for in case of the reverse reaction, that will be basically the positions of the reactants and products will be altered, means it will be interchanged, right? So therefore it will be, the denominator terms will come in the numerator, and the numerator terms will come in the denominator. Therefore for the reverse reaction, the Kp value will be basically the reciprocal of the forward reaction. Okay, so that you have to understand. I guess you get it. Okay. Next. Next one. The larger the Kp, the larger the constant, that is equilibrium constant, the more complete the reaction. Okay. So one idea we will get from this. That means if we study the values of Kp, then we will get one idea that how far the reaction will be, how far the reaction will be complete. So if the Kp value is large, then it will be towards, more towards completion. Okay, but more means what? There is means how more is more basically. So there may be a confusion. So to understand that, there is a particular guideline that with Kp greater than 1000. Okay, that is one guideline. So if, let me write here, if Kp is greater than 1000, or basically natural log of Kp, that is basically tabulated values, is greater than 7, is usually assumed to proceed to completion. That is it almost complete. Complete means fully converted to products. Assumed to proceed to completion. Okay. Next, if Kp is less than 10 to the power, as it is greater than 10 to the power 3. Similarly, if Kp is less than 10 to the power minus 3, then we consider that, or say ln of Kp is less than minus 7, then we consider that the reaction does not take place at all. That means if for a particular reaction Kp is more than 1000, then we consider that almost 100% reactants are converted to products. And if Kp is less than 10 to the power minus 3, then we consider that the reactants does not react at all. Okay, so you will see in the chart that for a particular reaction, the Kp value depends on temperature, and sometimes a same reaction does not take place at all when the temperature is, say, very small. Okay, and at a high temperature, the reaction is almost complete, like that. So here you see one reaction. Here you see one reaction, sample reaction for hydrogen converted to hydrogen atom. You see that at 1000 Kelvin, what is the value of Kp? Kp is 5.17 10 to the power minus 18. So 5.17 10 to the power minus 18. That means the percentage of hydrogen atom converted is 0. That means at 1000 Kelvin, hydrogen dissociation is 0. Again, at say 6000 Kelvin, you see the hydrogen dissociation is 99.63%. So from this, what you get, what idea you get, that if you want to convert, or if you want to achieve some chemical reaction, how much achievement or how much conversion you need depends on the temperature at which the reaction has to be conducted. Okay, so from the chart, you will get the idea that what is the Kp value and corresponding what will be the percentage conversion. So that is to be kept in mind. That reactions, so far reactions according to the first law or the mass conservation, that gives us only the reaction, that means that may take place, but at which temperature and how much it will be converted, that idea we did not get. So far we did not consider the chemical equilibrium. Here we get this idea that how much it will be possible. Again, we will see later that it is giving you only how much it will be converted, but how fast it will be converted, you will get no idea. Okay, so that also you have to keep in mind. One chemical reaction may take, say, years to complete. That is so very slow. The chance is the conversion may be 100%, but the reaction may be very slow. So that also you have to keep in mind. It gives you the rate of it gives you the amount of conversion, but the rate of conversion is not given by Kp. Okay, so that also is important. The rate of reaction is not given by Kp. So the larger the Kp, the more complete the reaction. If the equilibrium composition consists largely of product gases, the partial pressures of the products are considerably larger than the partial pressure of the reactants. So the partial pressure of the product will be higher, definitely, if the equilibrium composition, that means depending on the value of Kp, if the composition contains mainly products, so partial pressure accordingly, because the number of moles of the, say for example, reactants completely converted to products, therefore the presence of product is almost 100%, therefore the partial pressure of product will be almost means that is maximum, almost 100%, therefore the presence of the reactant will be almost zero, therefore the Kp value will go towards infinity. right? Because it gives it is the partial pressure and the ratio of partial pressure of the products divided by the partial pressure of the reactants, definitely raised by their stoichiometric coefficients. So Kp value will be large. Okay. And in the reverse case, Kp value will be very small or negligible. Okay. Next one, point 4. Fourth observation. The mixture pressure affects the equilibrium composition, although it does not affect the equilibrium constant. So now we will see this one very importantly. Very closely we will try to see point 4. In point 1, what we had seen is that the Kp value is dependent on temperature, it is not dependent on pressure. So Kp is not pressure dependent. But if the pressure changes, you see that here 1 atmosphere, here 5 atmosphere, here it is 3 atmosphere, here it is 2 atmosphere. So in the fourth point, it is said that if the total pressure is changed, definitely the partial pressures will also change. And the equilibrium composition will also change. But the Kp value will not change. Kp value at a particular temperature is fixed. So if you change the total pressure, what will happen? The partial pressures will change and the chemical composition, that is the number of moles of the composition, will also change. They will adjust their quantities in such a way that the Kp value will remain constant. So how to do it? How it will be done? Try to see this. That here you see Kp and here you see that the total pressure is, if the total pressure is changed, partial pressure will also change. Now, at a specified temperature, Kp value of a reaction, and thus the right hand side of equation 1615, this one, right hand side will be constant. So Kp value is constant. So remains constant. Therefore, the mole numbers of the reactants and the products must change to counteract any change in the pressure term. So what is the meaning? The number of moles, of the reactants and the products must change to counteract any changes in the pressure term. So pressure term will change and the number of moles will change accordingly, so that the change in the pressure will be counteracted by the number of moles. That is the point. So you see this one. This one. So if the total pressure, see this term, last one. So total pressure is changed. So this will change, right? Now you see that this is known, this is constant. This is known, means for a particular reaction, this is known. So delta nu is known. It may be positive, it may be negative, it may be zero. Three conditions are possible. But if you change the total pressure, so accordingly, this term will either increase, that is P to the power delta nu will either increase or decrease or unaltered. So if it increases, the numerator term will increase. Therefore, what will happen? To make the Kp constant, the denominator term must increase compared to the numerator. So what will happen? The reaction will be moved or shifted towards the the chemical reaction will be shifted towards the reactants. So number of moles of reactants will increase and number of moles of product will decrease. Therefore, the increase, that means what? In case of delta nu is positive. In the case when the delta nu is positive, then in that case, the if I increase pressure, then the number of moles of the reactants will increase in the equilibrium composition compared to the number of moles of the products. Therefore, the denominator will increase and the numerator will decrease, and this term will decrease and this term will increase. The composition, accordingly, the value of Kp will be kept constant. Okay, so if I increase the pressure, so increase in pressure results in what? Therefore, increase in pressure results in changing the partial pressures and the chemical composition, because partial pressure also changes and the chemical composition, that is the relative values of the reactants and the products will change, and therefore the Kp value will remain constant. Anyone asking anything? I cannot see. Okay. Okay. Actually, I cannot see anyone if anyone is asking. Okay. Next. Next one, okay. So if the Kp value, that means pressure is changed, then it will change the equilibrium composition, although it does not affect the equilibrium constant. That means equilibrium constant will not be affected always, because it depends on temperature only. Unless the temperature is changed, that will not change. Okay, it will only change the equilibrium composition and the partial pressures. The fifth one. The presence of inert gases affect the equilibrium composition, although it does not affect the equilibrium constant. Again, in the first point itself, we have mentioned that if we have some inert gas present in the equilibrium composition or in the reactants, that will not undergo any reaction. Therefore, that will not change the equilibrium composition. But it will, that will not change the equilibrium constant, but definitely the presence of inert gas will affect the equilibrium composition, because that is one component that is present in the composition. So definitely the equilibrium composition will be affected. That means in one case when there is no inert gas, and in the second case when there is inert gas, definitely the compositions are different. So the presence of inert gas definitely will change the equilibrium composition. However, it will not change the equilibrium constant value, because that is not going to give you any effective value of delta G star T. Okay, so that we have seen. But it will change the equilibrium composition. How it changes? Because you see that if you increase or if you just consider having some inert gas in the equilibrium, that is equilibrium mixture, then the total number of mole will change. Here you see the total number of moles will change. Okay. Now, okay, in the previous case, I forgot to mention that if you have this P increased, but this is a negative. So in that case, what will happen? The change will be in the opposite direction. That means in that case, that means pressure is increased, but delta V or delta nu is negative. In that case, the product will increase and the reactant will decrease, because in that case P will be in the P effective will come in the denominator. So P to the power delta nu, it will come in the denominator, and therefore this will increase. Therefore, to make Kp constant, we have to adjust this. That means that we have to increase this compared to this. Therefore, the products will increase and the reactants composition in the composition reactant will decrease. Therefore, the reaction will be shifted towards the product side. Okay, and when this is say 0, in that case, the change of pressure will have no effect on the equilibrium composition. Say, for example, 1 mole of A, 1 mole of B is reacted to produce 1 mole of C and 1 mole of D. So effectively, the total number of mole is conserved, as if total number of mole is unchanged. Therefore, in that case, the pressure will have no effect. The change of pressure will have no effect. Okay, that there are three possibilities. So for the fifth case also there will be three possibilities. If we just have some inert gas present in the equilibrium mixture, in that case, depending on the value of delta nu, whether it is positive, negative, or zero, depending on that, if we have some gas, inert gas present in that mixture, then if it is positive, that means if it is positive, that means this will increase the denominator. That so adjust this, we need to increase this compared to this. That means in the equilibrium mixture, the percentage of the products will be more. That means if I insert or if I just give some inert gas or introduce some inert gas in the mixture, so the reaction will shift towards the products. Similarly, if we have this term negative, in that case, introduction of inert gas will shift the reaction towards the reactants. And if this is zero, in that case, introduction of inert gas will have no effect in the final composition. So without inert gas and with inert gas, the equilibrium composition will be same. If delta nu is zero, that means for the case when you have say 1 mole of A plus 1 mole of B is producing 1 mole of C and 1 mole of D. In that case, introduction of inert gas will not affect the final equilibrium composition. So this is the fifth observation. So in this case, you get some idea that if you want to shift a reaction towards completion, then how the effect of inert gas can play roles. Okay. Now, point 6, when the stoichiometric coefficients are doubled, the value of Kp will be squared. That is quite obvious because you see that the Kp value depends on the stoichiometric coefficient. Therefore, if we change, say in any, basically any reaction, if we change the or make the stoichiometric coefficients double, then the Kp value will be squared basically. So here you can see that you just change them to double. So whole it will be to the power of 2 increased. So Kp will be Kp square. So if you just make these all 2, Kp will become Kp square. Like this. So here it will become Kp square. Okay. Next. Yes. Some other observations. Free electrons in the equilibrium composition can be treated as ideal gas. So here, at a very high temperature, usually about 2500 Kelvin, the gas molecules will start to dissociate, and they will be basically in the form of atoms. And at further higher temperature, the atoms will lose easily the electrons and they will be ionized. So in that case also the ions the free electrons in that state can be considered like ideal gases. And accordingly, you can write the KPs for that ionization situations also, not only just formal chemical reactions. For ionization situations also, you can basically write the same equilibrium constant values. Okay. Next, equilibrium calculations provide information on the equilibrium composition of a reaction, not on the rate of the reaction. That I have mentioned earlier also, that it gives you that how much it will be complete, or how much will be the composition, what will be the exact composition at the equilibrium state, or equilibrium means chemical equilibrium when it will be achieved, what will be the composition, but it will not give you the rate of reaction. That means how fast the equilibrium will be reached, or how fast the chemical equilibrium will be achieved. That will not be possible to be known from the equilibrium calculation. Okay. Sometimes it may take years to achieve the indicated equilibrium composition. So as if it may appear that the reaction will be complete, but it may take a long time. So that idea you will not get from the equilibrium calculations. Okay, but you can basically alter the rate of reaction by introducing suitable catalyst. Okay, that is not part of this. So that means this kind of changing of the rate of reaction, that is not definitely part of this here. Only we are considering the calculations regarding the chemical equilibrium and equilibrium constants, etc., and related composition calculation. Okay.